Sorry?
Probably won't stay now.
You got it? Yeah, yeah. Cool.
Can only stay.
Okay, so as you can see, question 3. Well, first it's asking you to state Lagrange's theorem. I mean, it's something we expect you to be able to give an accurate statement of from memory. And then part B is kind of like a guiding you through the proof of it. Asking you for relevant definitions and, feeding you the key intermediate stages to. And then part C is an application of it. Quite an important application of Lagrange's theorem that every group of prime order is. Okay. Any questions just about the questions?
No.
Yes. Okay. So, what would we write for this? Take Lagrange's theorem on the orders of subgroups of a finite group. Already quite, a bit of prompting in the question. How would you state this? Say that H be a subgroup. My favorite kinds of things. So that H be a subgroup of a finite group G. Can you all remember what the statement is? That's what Lagrange's theorem tells us. The order of the subgroup is a factor of or divides the group. Yeah. And order of H divides the order of G. We're assuming G is finite, these are just finite integers. Okay. Anybody full marks going for that? Much? And it's it's something that restricts the possibilities of okay, state the definition of the left and right cosets of H and G. Again, it's pretty standard bookwork stuff. Okay, so a left coset, which we write as GH of H and G, is a set GH which consists of all products little g times H, as the H ranges over all the elements of H, and we should say where G is one particular choice of element. Okay. To conform one of these left cosets, say, did we normally say generated? No, I don't think you said generated by G. Responding to G, or have any phraseology for that?
Coset of G.
Represented by little g. But the coset of. Well, when we say the coset of H and G.
You say it's coset.
I think you used to use the word representative.
Yeah.
Representative of H.
Well, that's okay. I mean,
Yeah. No, there's nothing missing there, but. Yeah. Representative, I guess, fits in with the general terminology of equivalence. Does everyone agree that's a good definition of left coset?
there was before you put it in my ticket.
Okay. Then, and then a right coset, similarly. Right coset. Set. Which consists of all products H, against H ranges over H. And that may or may not, of course, abelian groups, the distinction isn't there, but the same. But in non-abelian groups, these could well be different and typically would be different. some special feature. Say things.
It's called normal.
Well, oh yeah. But normal is special.
Normal is special.
Yeah, that's a strange thing to say, but it's true. Okay. It's not it's typical behavior. No, it's not. No, it's normal is
Nothing.
special. Okay, should we proceed? Does that spark any questions in your mind or?
No, this
or
is
just-
all-
Yeah, okay.
Thingy.
Very faithful before.
Yeah, that's quite. Okay, so now it's starting to ask for a little bit of proof. So we're looking at two cosets. So we're focusing on left cosets now. Two left cosets, and it's asking us to prove they're either equal or disjoint. Sorry. Oh, they can't see the question. Sorry. So we let G1 and G2, the elements of G, prove that they're either the same or disjoint. Okay? So this is in the picture you have in your mind of the group G partitioned by the cosets. Well, this is the key part in proving that the different subsets in the partition don't overlap. Okay, they're either exactly the same subset, you've just chosen two different representatives on the same coset, or they're have partial. Okay, well now, as is often the case where the conclusion you're trying to prove is an or statement, a disjunction, that in effect gives you an extra assumption because you assume the negation of one of them and show that that implies the other one.
Yeah.
Remember that classic case of them proving Euclid's lemma in number theory that P divides AB, then P divides A or P divides B.
Mhm.
And you effectively give yourself the assumption P does not divide A, show that implies.
Here, that's it.
I mean, in first year logic, it came down to that the definition in some ways of A or B that was defined as not A implies B, or
Not being
not B
implies
implies not.
Yeah.
So that's what we do here. Maybe G1H intersect G2H is the empty set. So the result holds. There's nothing more that would be required to prove. Otherwise, it is empty. It is not empty. Otherwise, intersection not empty. So we can let X be an element of the intersection. So if the intersection not being empty is somehow significant, we should immediately grab. Let's inspect the things in the intersection. So we take one of the elements. So now it's clear, or now what our strategy should be, now we're trying to prove the other part of the OR statement. So that G1H is equal to G2H. Is this leaving a gap kind of thing? The conclusion in this part is to conclude that the G1H is equal to G2H. And remember the general kind of mode of attack if you want to show, these are after all just subsets of G, that this subset is equal to this subset. General kind of mode.
It's all like backwards engineering.
Yeah, that's, remember I did this in number theory a lot,
Yeah.
kind of put the conclusion down here and try and draw
Bridge
it
the
back
gap.
toward, bridge the gap, exactly. So how do we normally show that one set is equal to another? Well, it's to show we can take the first one and show it must be a subset of the second one, and vice versa. Take the second one, show it must be a subset of the first. That's normally a good systematic way of, and if you can show that, then that shows the two subsets or two sets are equal. So that tells us we can, so that gives us kind of two little arguments to produce here. So that G1H is contained in G2H and vice versa, G2H is contained in G1. Now we ought to unravel this. Okay, we've taken an element X in the intersection, but that tells us a little bit more about what's going on. Because it's in the left coset and it's in the right coset. So that we can say then that that X is G1 H1, and it is also simultaneously G2 H2. For some choice, for some pair of elements, H1 and H2. Okay. We're going to use that in two versions. Now I'm going to take a Y, take any element in G1H, i.e. Y is equal to G1H, some H. And I want to show it's in G2. See, I can take this equation up here. I can see that I can write G1 as in a nice way, as G2 followed by elements in H. So I can write this as G2, H2, H1, H, and that's true since G1 is equal to G2, H2, H1, H1 inverse. Yeah. Does that make sense?
Is that last H just singular H? Is it like there's no
That last
to it?
That last H is the one that generates the Y. Yeah, I'm kind of taking a general element from the left coset.
Yeah.
So, yeah. And of course, what you're looking at here, this triple product, of course, is an element. H is a subgroup. So this element here, so we could say then, so Y is definitely an element of the left coset G2H. And there's nothing special about Y. Y was general element there, so it's now in here. And hence, we could say that the left coset G1H is contained in the left coset G2. Similarly, then, we could show the inclusion the other way around. Yeah. Since it's effectively the same argument, I can afford to be a bit briefer. If Y is an element of G2H, i.e. Y is equal to G2 little h, then we can write that G2 is going to be G1, H1, 2 inverse H, which is again an element of so everything in G2H is necessarily in G1H, so G2H is contained within G1. And if you've reached both inclusions, first set is in the second, and the second set is subset of the first, then you can conclude the two subsets. Okay, but it all turns on identifying one of these elements in the intersection, and that gives you interesting elements H1 and H2, which show you that, which allow you to move from one coset into the other one, so to speak. So So that proves, I mean, maybe just give one final conclusion statement saying, you know, therefore, one of the two must hold. Either the intersection is empty or it's not. Is that okay?
Yeah.
And that's the way to do it. I mean, you might think you could equally well prove it by assuming the negation of G1H equals G2H, and try that implies this one here. But that, I think that would be quite awkward to do, or I think you'd effectively end up, you know, I don't think it would fall down onto the page quite as nicely if you assumed that G1H was not equal to G2H, and then tried to prove that necessarily implied that the intersection was empty. You probably end up somehow coming back to this kind of argument again, be it proof by contradiction or something. So this is the more natural way to do it.
Seems nice.
Yeah.
Seems like it's so close to the page.
Yeah. Okay.
Yeah.
Any related questions to that, or seem fine? Part 3. So we now have a picture. At this stage, we now have a picture of the group G. Well, kind of. We still have to say a little bit, say effectively that it's reflexive, but we can kind of think now of G as partitioned into the left cosets. Okay? We count all the elements in G by counting the elements coset by coset. Okay? And then this is the next crucial step. In fact, they all have the same number of elements. The total number in G will just be a multiple of the size of 1. Okay, 3 is asking us to prove that. Prove that all cosets of H and G contain the same number of elements. Remember how we did that? Yeah.
That's just what
Yeah.
you say by objective map.
Yeah. In this kind of discrete D mathematics approach, you know, proving things are the same size. You know, kind of everywhere.
Yeah.
Psi, you know, that's the central kind of principle is
That's the
that.
definition of being same size.
Yeah. Yeah, it is. Yeah. Existence of a bijection between the sets. Okay. So what you do when you're counting objects, you're exhibiting a bijection between the objects and the sequence of natural numbers up to some point, you know, 1, 2, 3. You're associating the 1, 2, 3 with each other, with the objects.
Yeah.
So you're calling out the bijection when you count things in a naive way. But it extends to the general principle as well. So we need a bijection. Well, we need a bijection in principle, supposedly between any 2 cosets. But we can do that by showing that they're all bijective to some central reference. What's that? Which coset is special? Well, maybe not. Yeah. Okay, yeah, let's go for it. Yeah. The T1H, T2H, B2 cosets. Consider the mapping. So first of all, we need to define our mapping. Theta is going to be from G1H to G2H. Defined by. Okay, so we got to be able to say what value it takes on a typical element of the domain. So which element of G2H is this going to be? Well, So I wanted,
G1, G2, H implied by that.
yeah,
That would be,
definitely wanted to drop into the set. So it has to be G2 followed by an element of H. Which element of H?
Yeah.
well, I mean,
Good,
you're stretching it a bit.
but that's,
like 3 total X.
actually do it that way.
Well, this one. Yeah, well, because you have to say how you get the H anyway. So,
Well, that's what typical elements look like.
yeah. I would do it, but you go.
Carry on. So there's
Because Jordan is saying the right thing, the inverse. That's it. Right.
yeah. Normally, you know, some
But-
associated element.
Would be the inverse of anything. So, okay, so I will put G2,
Okay,
G1 inverse,
let's go for that.
G1H.
T1 inverse G.
No, you can think, you carry on.
Yeah, well,
You
okay,
have the-
so,
I would put G2, G1 inverse, G1. What you put.
so I just put H there.
But in fact, it's going on. So multiplying each element of the first coset with G2, G1 inverse.
Yeah.
I don't know, in my mind, that was.
Yeah.
More.
Jan's thinking about it more dynamically, that there's some kind of operation or process you apply to the elements in this coset. Yeah, you always did that with it.
No, but I think,
But-
well, okay.
Okay, so let me just complete my version.
So I'll tell you what the advantage of my version is as soon as you.
Okay. So the way I'm laying it out here is I say, so we need to define what theta is on a typical element from the domain. So I'm saying that a typical element of the domain is of the form G1H, some H, some little h, and I'm simply going to map that to the element G2H. Okay, yeah.
Then I will essentially go into.
I mean, you could quibble and say, well, how do I know that this choice of H is unique? Because
Exactly.
mappings have to be uniquely defined. But
Either the H is unique, which is the case. Or
so you would say defined by
theta
so
of X.
theta of X equals G2.
G2, G1 inverse. G1. Now, at least it's clear in my version that it's well defined.
Yeah.
It's an element of,
Well, we
it's
don't
definitely an element of G.
definitely
And
to G.
because every X is of the form G1 times H is also.
There's, I mean, it's definitely in the group, it's just a product of elements in the group. It's definitely uniquely defined. X is the argument, and X turns up there. The product, and these G2 and G1 inverse are constants. And then the observation is that this, you then observe that the X is equal to G1H.
Therefore, it's
G1H for some H. And then it becomes clear that this is an element of G2H. G1,
yeah, it's in terms of identity.
G1, it cancels.
Cancel out.
Yeah. Okay. I'm going to go with Jan. I like Jan.
So
I'm increasingly finding I do have to defer to Jan. I mean, yeah, it deals nicely with the.
In your version, you have to argue either that H is
Yeah.
unique for each element of the coset, which is true.
Which is true by the.
It's true, but
cancellation.
or that it doesn't matter which we do.
Yeah.
Sure.
Which it doesn't because it's.
Yeah.
But we have to say, so essentially you put it down to. No difference.
Yeah. The style,
Just leave it as.
Okay, so there's our mapping. So remember, we're trying to prove they're all of the same size. So we need this to be a bijection. Okay. Theta is injective. So if it's injective, we have to countenance possibility that theta of x1 is equal to theta of x2. That would imply that, so we use this rule here, G2, G1 inverse x1 equals G2, G1 inverse x2. But then we can use the cancellation law. You got the same element in the same position, both sides, you can strike it off. Yeah. So that implies x1 equals x2 by cancellation law. And that's injectivity.
Oh, X1. What is it?
And it's surjective since here's where we might circle back to see some advantage in my definition. Since theta of what is, because to be surjective, you've got to show that you get all the elements in the codomain. So which element gets sent to G2H?
You.
Feed G1H into this definition of theta. So you got G2, G1 inverse G1H, so you get. You satisfied by that?
Yeah.
Yeah.
And then obviously that element.
Yeah. So this is the thing that gets sent to that.
So is it both injective and surjective? If both, it then means that it is bijective.
Bijective, yeah. Theta is a bijection. And the conclusion from that is that the two sets have the same number of elements. They certainly have a finite number of elements because they're going inside a finite set. G is finite in all of this. So the size of G1H is equal to the other way you could the other thing I said before when I was saying show that there's always a bijection to a reference set. That was showing. You can see the map. Still call it theta, because it's the same map. This map going from H to G1H, and that would be defined by sending the element little h to G1H. That's effectively the same map, yeah.
Mm-hmm.
So the conclusion there would be that every coset has the size of this particular coset H, but they've all got the same size as that one. That means they all have the same size.
Yeah.
Namely that one.
Just mapped it with.
I mean, yeah. I mean, it's the same map as up here because here the representative is the identity element.
Yeah.
EH, so it's effectively the same.
Yeah.
Same. You still have to show that it's injective and surjective. Just a bracket. Yeah. Okay, so that shows they have the same number of elements. Okay. Ready for part 4? Show how the parts 2 and 3 above can be used to prove Lagrange's theorem. I mean, I quite like to give a little sketch here. Cosets, coset H, another coset 1H, etc., etc. Particular sketch. We can say G is partitioned by the left cosets. GH as G ranges over the elements little g. Since for all G in G, G is an element of the coset represented by itself. And by part 2, we're referencing the earlier parts, by part 2, different cosets are disjoint. Okay, so that establishes that it's a partition. That establishes that it's a partition. Agreed?
Yeah.
So then, the basic principle is that so the elements of G can be counted according to this partition. And by part 3, all subsets have the same number of elements. They all have the order of H elements. Yeah. Subsets of order of H elements. So the order of G is equal to m times the order of H. M equals the number of left cosets. Which is equal to the index of H and G. Or that's what we call the index of H and G. So m is an integer because m is just a count to the number of subsets that there are. So that shows the divisibility. Lagrange's theorem is true. Sorry. So there's still 5 marks going for part C, which is this nice application of Lagrange's theorem. Because G is a group of prime order. Lagrange's theorem to show that G is cyclic. So you definitely want to think clearly that you know the definition of cyclic. So we're looking to prove that G is a generator. Yep. So suppose the order of G equals P, where P is prime. Now, certainly P is strictly bigger than 1. Yeah? Why am I saying that?
Because the smallest element of a prime is 2.
Smallest prime, yeah. So that's what allows me to say that.
Yeah.
The smallest prime is 2.
But then there was another thing that we also mentioned to say that we can't have P as 0. Because if we do P minus 1, it would be 0. In this case, if we said it could be equal to 1.
Oh, yeah.
That was the other thing I could remember.
Yeah.
Anything more specific than that?
Well, so now we know G. So now we know the order of G is bigger than 1. So this means I can point now to a non-identity element. So if the order of G was just 1, it would be cyclic and it would be trivial. The only thing in it would be the identity element. But since P is greater than 1, so G is non-trivial.
To imply that remark that it's non-trivial.
It's non-trivial. Yeah, it's got the identity and at least one non-identity element. So let X be a non-identity element from G. So X is a non-identity element from G, and I consider there is a subgroup, there is a cyclic subgroup of G. This is the cyclic subgroup generated by X. Write it down, show it. It's the identity, it's X squared, it's X cubed, and so on. Okay, it's all the powers of X.
If we were in an infinite group, we'd have to write the cyclic subgroup generated by X and include all the negative powers as well, if we were in an infinite group. But because we're in a finite group, but they don't have to be. Because it's a finite group, I know if I just look at the positive powers of X, I'll encounter all the inverses. The sequence of powers will have to repeat at some stage. We're inside a finite group.
Yeah.
It can't go on to be distinct elements forever. So it will repeat, and it actually cycles back and gives you, so some X to the power n is actually equal to the identity. X to the n minus 1 is the identity of X, is the inverse of X. X to the n minus 2 is the inverse of X squared, and so on.
Okay, but let's not beat about the bush too much. By Lagrange's theorem. Oh yeah, and the point here is that the size of this subgroup is greater than or equal to 2. Because it at least contains the identity in X. Maybe X squared is already back to the identity again. Maybe it only contains 2 things. But it is at least bigger than 2. 2 or bigger.
It's going to sound silly, but the generated group by X, you've got identity X, X squared, X cubed. Does that go to XP minus 1? Or
well, we don't know how far it goes because we don't know the order of X at this point.
Yeah.
We're about to discover it. But it will go, yeah, so the answer is it will go to X to the P minus 1. It's the last element. So in total then you'll have P elements. Yeah. But we don't know that yet. So we can prove it. So by Lagrange's theorem, the order of X divides P. So the order of X is equal to 1 more P prime. Prime numbers only have 2 positive divisors. So that means the order of x is equal to p as already, sorry, the order of x, as we've already remarked that the order of x is bigger than 2. So this subgroup of G has P elements in it, but G only has P elements in it. So what have we proved? We proved, and we know automatically, we always know that X is contained in G. The cyclic subgroup generated by X is a subset of G. But now we know that there are P things in this subset. G only has P things in it. So it must be all of G, not actually a subset. Therefore, X is equal to G. And that's the conclusion. G is cyclic. That's the definition of cyclic group, a group that is generated by a single element. Is that okay for that question? I mean, we only got through one question, I guess. But
We can do the other one tomorrow.
yeah, we'll do some more tomorrow, definitely. Any related questions off of that? No?
As silly as this sounds, probably those answers that we give, they are completely 100% full marked. Like we will get the whole mark for those. They're not
These ones I've
abbreviated.
laid out
Yeah.
here, pretty well, it depends if it was Jan or me, Mark. Okay.
That's
No, but pretty much, I'll put the model solution up, but I think it'll be pretty much hit all those things as well. And I don't think we left out any point.
I was going to say any sort of defining description of what G is in any way, shape, or form in those particular questions.
No, I think we hit.
I
think we hit everything there. So those answers should attract full marks. Yeah.
That's a more eloquent way of putting it.
Okay.